Okay, now before we do our next sample problem, I'd like to do a recap on our first sample problem. And and our problem says that we have to design a horizontal screw conveyor to deliver 20 tons per hour. So take note this is given in terms of mass flow rate. And our material is rough rice over a distance of 24 meters, and we have these conditions. Okay, so the first step that we did is to obtain the necessary information. So since we know that it's rough rice, then what we did is we we go or we went to the material characteristic table. Okay, so we checked the material characteristics table, and for the rough rice, we found out that the the material code is 34 C1 half 35N. Okay, so 34 that correspond to the material density. This one is the size and the flowability, I guess, and this one is abrasiveness, and this one is the other properties. Okay, and it also, I mean, the table also tells us that the typical or recommended, I don't know if it's recommended, probably typical. So typical trough loading is 30%. A, the material factor is 0.6, and okay, we have this density. Okay, so after obtaining the necessary information, um, we compute the required capacity in terms of the volumetric flow rate. Okay, so by the way, I say volumetric flow rate, but what I mean is just it's volume divided by time. Okay, and okay, so 20,000, we convert that to the 2.2 pounds per kilograms, convert that to pounds, and then we multiply that to the reciprocal, or divide, you can just say divided by the density. Okay, and what you get is 1294 feet cube per hour. Just a couple of notes here. In our lecture handouts, we have these capacity factors. So this comes into play if you have other design of flights, like for example, ribbon flights, cut and fold flights, and if you have also like two-third pitch or short pitch. Okay, so there's gonna be some factors here. Actually, there's a lot of factors here that you are going to multiply. But for this type of problem, for this specific problem, since we have a standard pitch, then that's just 1.0. Standard pitch and standard flight. Okay, so after that, we went to the capacity table to select for the screw diameter. Okay, select screw diameter and of course an RPM. And in that table, so in that table, we first go to this trough loading, and then all the selections will be on this row, and we select a capacity that's greater than our required capacity. Okay, so we have this 1753, and we take note on the given maximum RPM. Okay, so we also know the data on the capacity, the capacity at maximum, and the capacity at 1 RPM. So after that, we solve for the actual speed, which is just simply the capacity, the required capacity, divided by the capacity per RPM, and we got this. Okay, so once you have this, um, that's actually we will need this speed if we are going to select for the drive. Okay, so if you have taken a course on machine design, then uh, you would know how to, I mean, the drive combinations, pulley combinations, or chain sprockets or gears. Then you will need this information. Okay, so for now, let's just write it uh, as it is. And what we did next is to check for the lamp size. Okay, so the lamp size is to check whether our selected diameter, screw diameter, is enough for the given lump, or for the lump size that we have. Okay, so since we are to assume that that's class 1, and we went to the table, the lump size ratio is 1.75. So what we did is we solved for the radial clearance. By the way, this radial clearance is, okay, so if this is our enclosure, this is our screw, then this is our shaft or the pipe, for example. So the radial clearance is this clearance. Okay, so with this clearance, computed clearance, we multiply the lump to the lump size ratio, and what we get is 0.875 inches radial clearance. That's the minimum. Okay, and then we went to this lump size table, and okay, we went to this radial clearance. Okay, so we have to find this 0.875, and that's actually less than this value right here. Okay, so meaning that our selected screw diameter is, okay, is far, oh, I mean, it is far greater than the minimum screw diameter required. Okay, so that's 14. So therefore, there's no need for the adjustment. Okay, so after that, what we did is to solve for the horsepower. First, we break it down into the components, and that's the first one is to solve for the friction horsepower. That's basically the horsepower required to drive an empty conveyor, and this is the equation. Okay, and we just substitute the values, and for the factors we went to the tables, the diameter factor and the bearing factor. Then we just select the values and then substitute in the equation, and then solve. Okay, so we got 0.385 horsepower. Okay, so the next step that we did is to solve for the material horsepower, and we substitute again. There's a given equation, and we just substitute the values for these factors right here. We just substituted the values from the table. Okay, and then you have this. And finally, for our total horsepower, we obtain this overload factor, then divided by this drive efficiency, and then we solve that we need a 5 horsepower electric motor. Okay, and after that, of course, in any design problem that we have, we need to provide a detail or a drawing, something like this, or better than this. Okay, you have to provide a much better pictorial or detailed view of the screw conveyor. Okay, and then just to practice our drawing skills, then I would like to have you draw the isometric view showing the details necessary. Alright, now we will do our next problem for this screw conveyor topic. By the way, I forgot here that you have to, of course, draw the drive. Okay, so you have to draw the drive and then the combination. Also, to specify this. Okay, so you have to specify if it's let's say 5 HP electric motor. Electric motor. Okay, so something like that, something complete, and that would be fine. Okay, so the next sample problem that we have is this one, and I have to draw it here. I forgot to draw. Okay, so we have a screw conveyor, something like this, and it's an inclined screw conveyor. We have this distance of 4 meters and a height of 3 meters. Okay, so the problem is we have a material that's shelled corn, and the pitch is short pitch. Okay, and what else? We have a motor reducer with coupling and a capacity of 1,800 feet cube. Okay, so that's the capacity, and a class 1 lump size. Okay, so let's solve. Again, first step is to obtain the necessary information. Okay, so if you go to the material code table, you'll find that for the shelled corn, you'll have material code 45C 1/2 to 5. Okay, and the density is 45 pounds per feet cube. This one, percent trough loading is equal to 45%, and a material factor F sub m is equal to 0.4. Okay, so the next step is to solve for the adjusted capacity. Okay, so why do we need to solve for this adjusted capacity? It's because we have a short pitch. Okay, so meaning we have to multiply that to a capacity factor. So CV rev, and let's just say that's adjusted, or we can just write an asterisk here. Okay, so that's adjusted. Okay, is equal to the CV required. Okay, by the way, what is this rev? That should be required. Okay, Q. Okay, required is just CV required. Okay, times the capacity factors. Okay, so what is this capacity factors? It's actually a product of many factors. CF1 times CF2 times CF3 times CF4. Right? So you can go to page 17 and it shows there the page 17 of the catalog. So you will you'll find tables for CF1 special screw pitch capacity factors. So if you have a standard, you have a capacity factor of 1.0. If you have short, then you have to multiply that to 1.5, and if it's half, then 2.0. For long, this is 0.67. Okay, and if you have a special flight, let's say you have a cut flight or cut and folded flight, and then depending upon the loadings, then you'll have um, to to take into account these factors. Okay, and for the CF3, you also have that's ribbon screw capacity. Okay, so if you have a ribbon flight and if you have a paddle flight, then you have to take account to the you have to take into account those factors. Okay, so for us, it's just 1.5. Okay, so CF1 is equal to 1.5. So therefore, CV uh, required is equal to 1,800 feet cube per hour times 1.5, and it's equal to 2,700 feet cube per hour. Okay, so the next step is to um, go to capacity table at 45% loading. Okay, so we have a 2,700, and of course we have to uh, look only in this rule, the 45% rule, and we have this. We can select this capacity, 2,813 capacity. So we can select a 12 inches, and then capacity of capacity at 1 RPM is equal to, that's 19.4. Okay, so now let's solve for the speed. Calculating the speed, that's just n is equal to CV required, the adjusted, times the of course noted for this capacity factor, time divided by CV at 1 RPM. So it's just 2,700 feet cube per hour divided by this 19.4 feet cube per hour per RPM. Okay, and what we get is okay, you can round it off to 140 RPM. Okay, so the next step is to check the lump size. Okay, so required clearance is equal to LR times the maximum lump size. Okay, I think I have to use this violet colored pen. Okay, so since this is class 1, then recall that it's just 1.75 times the maximum lump size, and since this is the symbol, then we have a lump size of, I think that's 1/2 inch. Okay, so 0.5 inches, and it's just the same as 0.875 inches clearance. Okay, and we see that this is that the minimum diameter is less than 6 inches, and therefore no need for adjustment. newtons. Okay, so the next step is to calculate the friction horsepower. So HPF is equal to L times N, times the diameter factor times the bearing factor, all over 1 million. Okay, so this length should be the length of the screw, and since this is just 3/4, I mean the size of the triangle, so this one would be just 5 meters. Okay, so 5 meters times 3.28. Okay, so that's 3.28 feet all over, I mean the conversion factor, that's meter, times the RPM, that's 140 RPM. Okay, times this diameter factor, that's 55, and this one we'll assume, okay, ball hanger bearing, so that's just 1.0 all over 1 times 10 to the 6, and we have 0.126 horsepower. Okay, so the next step is to calculate the material horsepower. Okay, so HPM is equal to CV required, of course the adjusted one, L times the factors. Okay, the flight factor, the material factor, what else? The puddle factor, over 1 times 10 to the 6. Okay, so this is 2,700. Okay, times 4 to 5, okay, times the length, 5 times 3.28, times, okay, so this is 1.0, this is 1, and this material factor is 0.4 times 10 to the 6, and we get 0.797 horsepower. Okay, so take note that we still have to solve for the total HP. Okay, total HP, and of course we're referring to horizontal position, or horizontal screw conveyor. Okay, so HP total is equal to HPF plus HPM times the overload factor all over E, the drive. Okay, so first we'll add this and then go to the graph. Okay, so our our friction horsepower plus material horsepower is this is 0.923. Okay, so if that's 0.923, this is it. Okay, so from this point you go upward and then go left, and that's 2 point that's 2.1. Okay, so 0.923 times 2.1 all over 0.95. Okay, so we get we have 2.04 HP. Okay, so this total horsepower is just the horsepower when it's in a horizontal position, but we have a situation wherein our screw conveyor is inclined at an angle. Okay, so we first have to solve for this angle, and this tangent theta is just equal to 3 all over 4, so theta is equal to 36.87 degrees. Okay, so um, what we'll do here for, I guess for simplicity purposes, we just use the trigonometric relations relating the power on this horizontal to the power on this inclined. Okay, so if we have power of HP is equal to 2.04, then what's going to be the HP on this incline? Okay, so HP incline is equal to the HP horizontal all over cosine theta. Okay, and what we get is 2.04 divided by cosine 36.87, 2.55 HP. Okay, so I guess the next available size would be 3 HP. Okay, so after that you have to provide the necessary details. Okay, so we have this diameter is equal to, what was that, to 12 inches. Okay, so 12 inches, and then our, okay, we can just write diameter of the screw and the diameter of the pipe. Of course, you can find that in the table. And what else? The pitch distance. So pitch is equal to 12 inches. Then the length is, okay, you have to provide that. It's 5 meters. What else? Speed, required speed, and HP. Okay, horsepower required. Okay, so our speed is 140 RPM, and this one is 3 HP. Okay, what else? We need to, again, just to practice our drawing skills, we have to draw this. We have to draw our screw conveyor. Or maybe using another paper would be, okay, so this is my, let's say this is my X, this is my Y, this is my Z. Okay. Okay, since we have a directly coupled drive, then that's gonna be something like this. Okay, and then you have to provide, for example, the support or something. I don't know, maybe something like that, or maybe with a brace, something like this. Okay, so that depends upon you as a designer. Okay, and then you just have to label the parts. Okay, so let's say the support, frame, brace, okay, and whatever, or drive. Okay, so now let's do a review on what we did in this sample problem number 2. We have a shelled core, short pitch, standard flight motor reducer with coupling. Required capacity is 1,800 cubic feet per hour plus 1 ball hammer bearing. Okay, we have a situation here that the screw conveyor is inclined at some angle, and of course we can find the total length because we are given with this two dimensions. Okay, so the first step that we did was we obtained the necessary information from the material characteristics table, and we write down the material code, density, the recommended or typical drop loading conditions. That's 4 to 5. And after that, we solve for the capacity, and In this problem, we solve for the adjusted capacity because our pitch is it's no longer standard pitch. It's a short pitch, so we have to multiply that to some capacity factors. Okay, so since we have short pitch only, and we're still in standard flights, then we just have to multiply that to the 1.5. Okay, so what we get is 2,750 per hour. Okay, so the next step we did is to we went to the capacity table, and at 45% loading, we selected a screw diameter, and of course we can obtain the capacity at 1 RPM. After that, we calculated the speed. We just divide that required capacity by the speed, and we obtain a value of 140 RPM. Okay, by the way, you might ask, why do we need to adjust this capacity? Okay, so we need to adjust this capacity simply because um, one revolution for a standard pitch would have a different capacity. I mean, different output. Okay, so that's why we need to multiply that to some factors. Okay, just to compensate the equivalent rotation or equivalent output per rotation. Okay, so after that we checked the lamp size and we found that it's okay, and then we calculated the horsepower. Okay, so in this horsepower, the total horsepower equation that we had was just for purely horizontal screw conveyor, and we have to find the the adjusted horsepower for the inclined, because once you're increasing the angle, you're actually reducing the capacity, and also um, you are requiring much power. So that is why the horsepower for an incline is greater than the horsepower if it's just in purely horizontal position. Okay, so what we did here was just a simple trigonometric relations. I don't know yet how they actually do it, because I haven't seen it also in the a catalog that we have, or maybe I haven't checked it out. But for simplicity's sakes, and this is just a classroom setting, so we just use the trigonometric relations. Anyway, it also makes sense that that your horsepower is increased from 2 HP, it increased to 2.5 HP. Okay, so somehow it makes sense as well. Okay, so after that, we have to draw our screw conveyor. Okay, so I guess that's all for this week, and in the next topic, we will discuss probably the belt conveyor or pneumatic conveyors. Okay, so see you next time.